So good afternoon. I hope you enjoyed your lunch. And people online, I hope you had a nice break. Our next session will be about intelligent mobility, autonomous mobility. We have two guest speakers from the University of Waterloo. They will talk to us about autonomous mobility, an overview of the Waterloo MVSLab's research work, what is known as Watonobus. I hope I'm saying it correctly. The speakers are Minghao Ning and Keki Xu. Minghao Ning received his bachelor degree in vehicle engineering from the Beijing Institute of Technology in China in year 2020. You're not that old. You look young. In 2020. He's currently pursuing his PhD degree under the supervision of Professor Amir Kajipur and Professor Hassan Hashemi with the Department of Mechanical and Mechatronics Engineering at the University of Waterloo. His research interests include multi-sensor fusion-based perception, motion planning, control, and cooperative perception systems. And Keki is a postdoctoral research fellow in the same department in mechanical and mechatronics engineering at the University of Waterloo. He completed his PhD and master's degree in mechanical and mechatronics engineering in the University of Waterloo, and his bachelor degree at Northwestern Polytechnical University in China. His research interests involve interactive planning and decision-making of autonomous vehicles. So welcome, guys. I turn it over to you. Please take it away. Thank you.
Okay, so yeah, we will share our screen.
Okay. So first of all, thanks a lot for giving us the chance to present our lab's work to all of you. So this is Minghao and me, and Kachi, that's me. So first of all, we would like to introduce our lab. We are the Mechatronic Vehicle System Lab. We have over 40 graduate students, postdoc engineers, and technicians, and is one of the world's largest vehicle control laboratories and a pioneering develop holistic vehicle control systems. So on the right, you can see that that's our group photo of our lab. And on the bottom side, that's all our fleet vehicles and our testing vehicle platforms. In the history, the current project that we have includes a vehicle control system, 5G autonomous fleet and mobility, autonomous urban vehicles, as well as robot and manufacturing or robotics projects. So and we have did a lot of old projects, for example, anti-idling, smart tires, etc., etc. And we're a very well-developed group, and I hope today's topic will bring your interest. So Minghao will give a further explanation of the work that we did.
Okay. Okay, so thanks, KG. And also, so today topic will mainly talk about our lab's work related to the autonomous mobility project. So basically, this is our summary here. So our project started like 6 years ago. We started with this single agent intelligence. So basically, we get a single bus there running autonomously, and then we get the license. And then we gradually try to develop the system to do the cooperative driving system. So basically, we try to put some intelligent sensor node to the road. And then the road is smart and it can give some perception result to the cloud, and then the vehicle can use this information. And we also have some tests related to the indoor sensor node project. So basically, we can control some robots and let it navigate in the indoor system. So yeah, we will first talk about this part for the autonomous driving part. This is our shuttle bus there. So basically, it runs along the ring road of University of Waterloo. So basically, it has 6 cameras and 3 lidars, and also 2 radars in front and rear. So it got one computer unit using the JSON ORIN, and also it's equipped with a very high accurate localization system using the Applanix RTK GPS navigation system. And also some interesting case in our scenario is that we get the pedestrian, cyclist vehicles, and also especially in Canada, we get the geese. So this is quite challenging, so we need to handle it properly. And also for our case, we want to run this whole system in all weather. So we also have some challenging case from challenging weather like the snowy day. So we will talk about our experience and how we going to address these issues. So this is a structure of our work. So basically, we get the perception and prediction part. We also have the decision making, which is the core of the whole system, where all information will be gathered and be processed here. And also, it's equipped with a high accuracy localization. And then the decision making will give some high level decision like whether to stop, go, and flower to the local plus planning. And then the low level control will give the steering angle and the speed control back to the hardware. And for the perception part, the overall structure is shown like this. So basically, we have 6 camera and 3 LiDAR there. So first, the LiDAR will be concatenated together using the high accuracy transformation. And also from the previous map, we get some rough position of the road boundaries. And then the image will be processed using optimized YOLO network. And also it will do a lane detection for the front center camera. For the LiDAR part, we will have developed adaptive grid ground removal, which basically we can adjust the tolerance for the ground removal part based on the distance. So we will get a very high accuracy for the near range, so we can make sure any tiny object on the road can be detected. And we also have a curb detection to make sure we will avoid running to the curb. And so this will be an example where we do the post-processing. We can precise use the information from the camera and LiDAR. We try to combine them together so we can get the 3D position and the class information for the objects. And in the end, we will try to combine the detection result, whether it's known and unknown. We also combine their class information back to this drivable space. So to make sure the bus will only drive in the allowed space, so just to increase the safety. And so first challenge we have is that for example from this challenge like this video shown, the heavy snow. So as you can see here, there are a lot of noise points are reflected from the snow. So we need to develop a method to try to remove this noise. So we just use some the information from the scanning pattern and also some intensity information. We have developed the tool to do this snow removal. So like this example shown. So the black points shows the noise points, and also in this case we get some comparison with some learning-based detection and also our method. So as you can see here, this near pedestrian is cannot be detected by some between the neural networks because there are a lot of noise near to this person, and then it's out of the training data domain, so it failed. But for our case, after we remove the noise, so we can detect this person very accurately. And also, there are some quite interesting or challenging cases. For example, which can be handled by the drivable space detection. So basically, for example, some like traffic cone and some keys on the road. And also, for this case, is that the map is outdated because there is a new construction there. So as shown as the yellow line, it's a prior map, but it's outdated. But after we do the curb detection and lane detection, we can accurately and make sure our Eagle bus can drive within this safe region. And also interesting case is from the snow pile. Is also as shown as the yellow line here is a prior map, but the snow pile is in the road. So we have to detect it properly to make sure our bus can drive safely. So this is an example how we use the driver space to address these issues. And there are some videos there to show the real-time performance. So basically, this is the crosswalk. So as you can see, the pedestrian are tracked properly, and the driver space show the prediction of their motions. So we will only drive within this safe region. So this is one example here, and also the crosswalk there. So there is another case is that in the snowy weather, as you can see, the pedestrians are still being detected very accurately and tracked accurately. The green arrows there show their prediction of their motion. So using all these techniques, so we can make sure we can get a very reliable detection and perception in these changing weathers. And then we can use the perception information and we can do some path planning. So this is a demo that we do a real-time plover. So yeah, as you can see here, it will try to plover at the bus stop region and it will open the door automatically. So if there is no pedestrian going on, so the door will be closed within 3 seconds. Okay, then it will try to merge back to the road. But as you can see, there is a car coming, so it will detect that using the fusion from the radar and the LiDAR and the camera, so it will detect that and it will stop the merging. And then after it's safe, it will continue to go back to the merge. Yes, so now, yeah, it will go to the merge state. So this is the whole demo for this part. And I think Kichi will talk about some game theories.
Yeah. So when we're operating the bus on the road, we found that sometimes when before the bus is considering other traffic participants as obstacles, and sometimes when there's a lot of traffic participants, or for example pedestrians, the bus has been had been full stop for a long time, and no one and the traffic is all stalled. And the reason to cause this issue is that the vehicle haven't considered that their behavior is influenced to the other traffic participants. It's only considered the influence of the other traffic participant to the ego vehicle. In this case, it causes a problem of called a freezing robot problem, where other pedestrians take advantage of this assumption of one-way interaction. So we developed a non-cooperative game in the decision-making process to eliminate this kind of a burden. So we considered not only our own benefits, but also the cooperation interaction among traffic participants. And to do this, in our formulation, we did a LQ game to address this issue. So we assign cost to each of the traffic participants, and also we model the behavior of this two-way interaction. So on the next slide, this is sort of when we're modeling the interaction, we want to find the realistic character so that we're not misguessing the behavior of other traffic participants. So we look for other open source data sets as well as the data that we collected on the ring road, and we find several key characters that represent a traffic participants and to properly model this interaction. For example, we extracted time to collision, we extracted the number smallest distance between traffic participants, as well as their nominal speed, and also as well as their yield or not yield scenarios, time to collision. So given all these extracted data as we presented on this table, we also been able to consider various type of driving characters. For example, different levels of aggressiveness, which also influence the interaction behavior, especially in the game formulation. So we're able to consider not only the strong interaction between robot and human, we're also able to consider the various characters of different traffic participants. Another thing that we also found while we're driving the bus is that there's sometimes the bus have to follow the rule to ensure that it's doing everything in the safe burden and aspect. So we also try to consider the traffic rule in this decision making or the behavior navigation of the bus. So when we consider rules, there's soft rules and hard rules. Hard rules are the things that we have to follow, which is traffic lights, stop signs, which we can usually hard code and we can consider in a more rigid way. However, there's some soft rules in the interaction process that also that are not, let's say, specifically written in the book or with a strict parameter. Therefore, in the interaction process, we also need to consider these soft rules to adapt to the behavior style or the nature of the interaction following the rules in this aspect. So, for example, we have pulling through unsignalized intersection, yield sign merging or turning vehicle, yield to oncoming vehicle at an intersection. So in order to consider this rule following interaction, we proposed a geometric way of representing the roadmap. For example, when we detect other when at the perception level, if we detect someone or some traffic participants at a certain area, for example, in this case at the crosswalk, then we know that all the vehicle that's within has not entered the intersection have to yield in this scenario. So this is sort of like a geometric projection from the traffic rule to our behavior with the geometric as a bridge in the middle. And in this setup, we're also able to deal with a very critical case when we're dealing with decision making in the shuttle bus at daily operation is the always stop sign. So with this setup, we're able to consider different forms of queuing, and we're able to manage and think of the interactions in this geometric setup. So overall, this is the interactive decision making of the shuttle bus. So for example, on the top figure, we have the perception model that gives us the state of the vehicle. Then we do a attention-based actor filter. This is the part that we only focus on the actors that are interacting with us, so we can improve our real-time performance. And then we estimate their behavioral style, for example, how aggressive they are, and then we know what parameters we can put into our game. And once we've done that, we also extract the traffic rule given our road geometry, and which in other ways tells us what kind of behavior or interaction type we are having, referencing to the traffic rule now. And then we'll have a sort of a right-of-way extracted right-of-way sequence. And given all these information, we're able to use all these information in our LQ game, which is the differential game, and we sort of figure out what's the optimal trajectory or the strong interaction considered behavior should we perform and send to the local controller, which is on the bottom left side of the figure. So this is the overall framework of the decision-making platform. And the next slide, we have some real-world testing results. That is, the first one is yielding to pedestrians. As we can see that this is a not very difficult task that the vehicle is able to yield to the pedestrian. On the right-hand side figure, that's the vehicle's planned path at every time step or a couple of time steps. And we can see that the vehicle is able to yield to the pedestrian, which is on the top with the history trajectory of the purple line demonstrated there, and it decreases speed and then increase the speed by yielding to the pedestrian. And on this next slide, we have a more complicated scenario with the vehicle's planned speed as the red line here, and the scenario is trying to stop at the OA stop sign. And then once the road is clear, it started to increase the speed and try to cross the intersection without any issue. One of the things that we could still look is that when there, in this case, that one vehicle is turning left. So this is a very complex scenario with the vehicle crossing, pedestrian crossing, as well as 100, let's say over 10 traffic participants in this scenario, and our planner is able, or our bus is able to operate in real time in this scenario, which shows that the algorithm that we develop is following the rule, is considering interaction, and is not, let's say, taking advantage by other traffic participants. And on the right-hand side, this is the planned path at different time step, which also demonstrate our ability of following the rule and properly interact with other traffic participants. So this is the shuttle bus part. And then Minghao will give a further explanation of how do we transfer from one single vehicle to the group networks of connected fleet smart vehicles.
Yeah, okay, thanks, KJ. Yeah. So the idea is that there's still some challenging case that the single perception is not able to handle everything. For example, imagine there is a huge bus in front of the autonomous vehicle, the sensor will be occluded by the obstacle in front. So you may not detect the obstacle behind that. So that's why we propose the idea of bringing the connected sensors. So we try to put some sensors on the road so we can enhance the safety. So as you can see here, so we get two types of projects. One is for the outdoor autonomous fleet. Another is for the indoor autonomous fleet mobility. So the idea is that we will want to try to improve the transportation safety and efficiency with this 5G connected intelligent sensor node. So then, for example, for now, the topology is that we will do some perception on each sensor node, and then you will try to send some information like the perception result information to the cloud, and then the cloud will merge all the perception, and it can have some API. For example, for the outdoor, we can do some traffic monitor, and we can also do some traffic safety warning. And for the indoor, we can do some asset management and also the navigation system. So first for the outdoor project, so we want to introduce our project called the co-infra, which means the cooperative infrastructure. So we have opened all the code in this GitHub link. So basically the project is that it includes 14 sensor nodes at the north campus of University of Waterloo. So for each sensor node, it will include sensors like one LiDAR, two cameras, and it also equipped with one computation unit. It's a Jetson Orin NX, and also each one has a 5G modem to get the real-time communication. And also we try to synchronize everything using the 5G based network. And it also has some IoT features like the power management, the OTA update and remote control, and also some realization. So just after each sentinel processes the data, it will try to send the result to the cloud, and then the cloud will fuse everything. And we will also want to introduce the dataset we have published recently, so focus on the adverse weather. And then in the end, we will briefly talk about one application that to try to evaluate the risk of the roundabout region, and we can give some warning there. So this is an example from, I think, last Thursday when there was a heavy snow in Waterloo region. So as you can see here, there are quite a lot of noise from the LiDAR part. And also you can see from the image part, there are some snow there. But the overall, this is the real-time performance from one of the sensor node. So as you can see, it can detect the cars very accurately. So for now, each sensor node can detect a range like 100 millisecond, in 100 meters. And this perception time just from getting the raw sensor to the time it can get the perception ready is around 60 milliseconds. So it's running, already real-time performance. And then this is another side from the center side where we can send each individual perception result from each sensor node, and we combine them in this cloud. So as you can see here, there are some vehicles that just traveling around this road. So you can see that we can get a very consistent tracking from one of the sensor node to the other sensor node. So this is the global perception. So we just try to combine all the results from each sensor node. So the overall time is that for now, each sensor node take 60 milliseconds for the processing. And for now, with the 5G network, the communication part take like 40 to 50 milliseconds. So the overall delay is around like 100 milliseconds also. And this is and we also have some IoT features like we can do this. We can have a UI to check the states for each sensor node, and we can turn on the sensors. We can turn on the LiDAR sensor and also the camera sensor remotely. And then we can also run the whole thing, the perception, the sensors, using this UI, and then we can check the real-time realization. And for the development part is that we get a group control, SSA control to make it easier to develop the code. So we can transfer the command to all the nodes. And also we get the power system monitor. So basically we can check the load and the solar panel voltage and also the battery voltage in real time through our UI. And then we would like to introduce our data set. So basically, this is the first large-scale multimodal data set collect under diverse and changing weather conditions. So as you can see here, we for this case, we only focus about the roundabout region. So we selected the sensor node, the 8th sensor node near to the roundabout. And for this case, we project the LiDAR and the camera information on this map. So you can see there are some overlap here. And also, why we designed this is like we want to make sure each part, especially for the roundabout region, can be at least covered by two sensors. This is to improve the safety of the whole system. So even if one of them is down, so the other can work as a backup. So as you can see here, for example, for this bicycle, so this cyclist here, it can be detected by this camera, and also this camera, and also it can be also detected by the three lidars for this corresponding sensor node. So this can improve the overall safety of the whole system. And also the data labeling part was done by customizing the open source data labeling platform, the CVAT. So we have customized this labeling part so we can overlay the point cloud and also the image. So as you can see here, we have first try to combine all the point cloud from all the sensor nodes, and we try to plot it on the HD map. But to make it easier to tell the class information, so we also try to overlay the camera information to this fake bird eye view. So with this feature, we can easily label the position and the class information for the obstacle here. And also this is one of the example, as you can see here. So this data can cover like the sunny day or night, and also some rainy day and heavy snow weather. One of the very interesting case is that for the freezing rain part. So as you can see here, this camera was very blurred by the accumulated ice, and also its LiDAR is also being covered by the is influenced by the ice. But based on our design, as I mentioned, each part is covered by at least two sensors. So even if one of these is down, we can have another sensor node as a backup. So it can still make sure the whole scenario is detected properly. And also for this data set, we can also have some very interesting cases, like I think whether researchers can use this to study the vehicle-vehicle interaction. For example, this is the real data collected from our sensor node. So as you can see, there are some vehicle yielding and waiting, and then go to this ring of the roundabout. And also there are some bus coming to this roundabout. So yeah, basically this is a quite dynamic and a complex scenario. So this data can be used to study the vehicle-vehicle interaction. And also on the right side, we also have some cases like to study for example, the vulnerable road users. For example, for this case is the pedestrian. The vehicle is interacting with the pedestrian here. So yeah, the vehicle try to slow down for the pedestrian and then it accelerate to pass to go into this roundabout. And also for this case, the person here, the truck is waiting for, and then after the person pass, the truck goes into this roundabout. So overall, this is quite interesting data set, and also some vehicle interaction here. Mhm. So yeah, so this page is a brief summary of the whole data set. So for now, we have around 100 sequences. So each sequence is around 25 seconds. So we get around 200K LiDAR frames and 400K camera frames. And also we get a lot of carefully labeled objects. And for the version 1, and for the version 2 is ongoing, that we want to combine the autonomous vehicle and also the intelligence sensor node. So we will also cover more data about covering the day and night. And also we have developed a system, we call it automatic edge case recording. So I will introduce later. And the target data size is around 1 TB. So for the version 1 is already like 250 GB. So now we want to make it larger. We are aiming to like 1 TB. And this is the distribution for the car, truck, bus, person, and bicycle, and the different weathers. So I think this is quite unique in Canada because we get a lot of challenging weather here. And so this is a brief UI for the automatic data logging system. Is that for each obstacle from the perception part, we have some basic rule-based driving behavior. So if for example, one of the car didn't follow the expected behavior, maybe there is something wrong that we didn't anticipate. So we call it as the edge case. So we'll try to record this sequence. So the idea is that from the sensor node part, we try to combine the perception result into the cloud, and we will try to calculate a score, whether based on the business or the similarity between the actual behavior and also the expected behavior. So we'll calculate this score. And when it's larger than a threshold, we will send the command to the sensor node, and it will try to automatically save the data. So then we can get a lot of very interesting and useful data through this system. And also, I think teacher will talk about the safety monitoring part.
Yes. So on the monitoring aspect, we found that runabout is one of the key elements in the safety of the road. For example, every year there is about at least in Waterloo there's over 100 accidents happening at runabout, and if we have those infrastructures, we're having a huge chance of at least find these edge cases where dangerous scenarios and try to have a have something to help people to well, at least help us to study those different cases of unsafe scenarios. And in this case, we are using a real-time monitoring of finding all kinds of different difficult scenarios, dangerous scenarios. For example, in this case, if a pedestrian is walking through the inner a crosswalk, then this is considered a dangerous scenario. And for example, if one vehicle is inside the ring and another vehicle is merging in, this is also considered as a dangerous scenario. And we use threshold, for example, as time to collision of how two vehicles are close to interact with each other. And if this time to collision difference is so small, then we consider that this is a nearly collision scenario, which will be labeled as a red mark. And all these interaction process will be saved in our back system and then will be studied for our next step research plan. And you can see that in this case, we have, for example, over 10 traffic participants in this scenario, and the real-time performance is really good. The toughest situation we only takes less than 10 milliseconds, and over that, I think that's over 2,000 or 5,000 scenarios that a time step that we evaluated, which shows that this has can respond very fast to the system, and which could be used on later evaluations. And now we also have developed let's say a first-person view of this scenario of how a monitor is operated. As we can see on the right-hand side figure, that in the real-world scenario with the vehicle running in real time, we have lots of vehicles. For example, in this case, it sees these two traffic. Let's say, for example, let's go back here. We can see that, for example, in this case, when it's heading towards the runabout, it might crosses the road over here, and there's a pedestrian here, so there is a chance that this vehicle might collide with that pedestrian. So we give that traffic participant as a red mark when we're merging in. And for example, take this vehicle as an example, when it's getting into the roundabout, it still sees a vehicle in front of him. Then in this case, there's a chance of a collision, and that therefore this traffic scenario is also recorded accordingly. So given this, we're able to find risky scenarios, which is also strong interaction scenarios, and therefore we can try to evaluate and find out characters in these and behind those behaviors. This is another aspect of the traffic pedestrians view. So we're not only considering how vehicle behave, but also how human behave. So we also extract all kind of different views and different interaction process, and that help us to further evaluate the interaction behaviors. And Minghao is gonna talk a little bit more on the indoor applications of our sensor node project.
Okay, yeah. So the idea is similar to the outdoor sensor node. So we try to put some sensor onto the wall or to the ceiling, so it can do some perception and can also combine the information. We can also do some cloud-based planning and control. So for now, we we focus on the healthcare area. So basically, we have developed some robots like the autonomous car and also the autonomous bed. So we try to. So the issue with this onboard sensor is that so each robot, the perception range is very limited. For example, at this case, so if you put one sensor in front of for example, this medical bed, it can only detect the range like this, as shown as this green one. So it may not be safe when it's a turn. So for example, like this case, for example, there is a pedestrian coming in this way. So there could be a collision case because the limited perception range. But if we put two sentinels like this, so it can cover the whole hallway and it will detect the person and robots very accurately in real time. So we can avoid this issue. And also another benefit for this Sentinel is that if when we put the Sentinel on the ceiling, it has a much better view. For example, like this, when it's looking from the top side, it can also get less occlusion. And also, when you have more robots operating in this scenario, the overall cost will be much less. For example, you can just put some good sensor on the ceilings, and then you only need to some very cheap and low-level sensors on the medical bed just to work as an emergency stop feature. And then for the high-level uh, functions like the navigation and other things, it can be done from the cloud. So this is the brief summary of the project. So we have put several sentinel like this. So for the 1, 2, 3, we will mainly start about the indoor navigation. And for this part, for the interaction testing tool, we will try to test the interaction between the robot and also the pedestrian. So the idea is similar to the outdoor sentinel. So we get some uh, perception tasks performed on each sentinel. So we get some camera detection, lidar processing, and then for one interesting case for the indoor application is that we will try to estimate the orientation information from for the human because the orientation matters. We want to do some social motion planning. So the idea is that we try to first do a 2D pose detection, and we use the camera pose information. We try to estimate the 3D position using using the 3D pose estimation using some, for example, some joint uncertainty and also some geometric coherence. And it can also, if the corresponding part has a point cloud management, it can also use that information. So we can just solve optimization problem, then we can get this 3D position estimation for the human pose, and then we can get the orientation information. And then this will be the local results. So we get the orientation and detection for the robot and also the human. Then we'll send this information to the cloud. Then the cloud will do some global fusion and some delay compensation using the estimated velocity. And then it will be used for the motion planning to do some obstacle avoidance. So this is a demo that we do the indoor navigation. This is the real-time operation. So each sensor node will do its own perception and send back to the cloud. The cloud will do the MPC tracking to just to follow this predefined route. And it will send back the control command back to this medical bed. So it will try to follow this very accurately and smoothly. And also, this is another case that the video is shared by Yufeng Yang, a PhD student from the same lab. So basically, after we get the orientation information for the pedestrian here, so we can study their interaction between the person and person and person and robot to make sure we can get a social comfort path planning in this narrow or in this crowded environment. So I think that's all our presentation. So would like to answer all the questions you have. And by the way, this is our supervisor, Professor Amir Kazipur.
Okay, I hope you hear me now. I'm just asking the audience here in the room to see if they have questions. Okay, I do have a question. Like, if you have, in the case of multi-sensors on the road, and they are overlapping, how do you synchronize them, calibrate them to the same real-world coordinates, and avoid, for instance, double counting cars? Like if one vehicle shows up in two sensors, how do you not perceive these as two vehicles, but essentially the same vehicle, and you hand it over from one to the other?
Okay, yeah. Okay, yeah, that's a very good question. So basically it will focus on two tasks. One is we want to trigger the sensor at the same time. So this is based on the 5G time synchronization, and all the sensor will be triggered based on the system time. And also for the other case, just we want to make sure, for example, for example, if one obstacle is left by two sentinel, we want to make sure they are the same obstacle. So this will rely on the calibration between the sentinel. So when we do the calibration, so we drive the bus there to scan a very high accuracy point cloud map, and then we try to align each sensor node back to this whole map in the global frame. So which makes sure all the sensor node is very accurately aligned with this global frame. So then when we do the fusion, so all the obstacle will be projected to the global frame. So then the same object will have a very high overlap. So we can make sure that the same object will only be used once. So they will be merged.
Excellent. And did you experience sensors drifting at all? Like, for instance, the calibration changes over time?
Yeah, so for our case, because we put the sensor on the light pole, so for now the calibration is pretty accurate. But I think you are right. So just imagine maybe there are some, for example, some winds. Maybe the calibration may change. So to fix that issue, we need to do some online alignment check. For example, just to do a ICP to try to match the point cloud with the whole map to make sure we get the very accurate calibration result. Yeah, I think, yeah, that's a very good question during the real application.
Sorry, I missed that. So do you recalibrate in real time? Like if a sensor is drifting, you recalibrate, or you have to stop everything and go out and adjust it? And
No. Because for now we just need to recalibrate, do the online recalibrate. We don't have to go outside because we just need to estimate the new transformation. We don't have to go outside.